Okay. And how do we make this model learn? Or how can we tell whether or not it's even learning? So before we talk about the models, let's talk about how can we actually evaluate these models, or how can we tell whether something is a good model or a bad model. So let's take a look at this data set. So this data set this is from a Pima Indian diabetes data set. And here we have different number of pregnancies, different glucose levels, blood pressure, skin thickness, insulin, BMI, age, and then the outcome, whether or not they have diabetes. 1 for they do, 0 for they don't. So here, all of these are quantitative features, right? Because they're all on some scale. So each row is a different sample in the data. So it's a different example. It's one person's data, and each row represents one person in this data set. Now each column represents a different feature. So this one here is some measure of blood pressure levels. And this one over here, as we mentioned, is the output label. So this one is whether or not they have diabetes. And as I mentioned, this is what we would call a feature vector because these are all of our features in one sample. And this is what's known as the target or the output for that feature vector. That's what we're trying to predict. And all of these together is our features matrix, X. And over here, this is our labels or targets vector, Y. So I've condensed this to a chocolate bar to kind of talk about some of the other concepts in machine learning. So over here we have our X, our features matrix, and over here this is our label Y. So each row of this will be fed into our model, right? And our model will make some sort of prediction. And what we do is we compare that prediction to the actual value of Y that we have in our labeled data set, because that's the whole point of supervised learning, is we can compare what our model is outputting to, oh, what is the truth actually? And then we can go back and we can adjust some things so that the next iteration we get closer to what the true value is. So that whole process here, the tinkering, okay, what's the difference? Where did we go wrong? That's what's known as training the model. Okay, so take this whole, chunk right here. Do we want to really put our entire chocolate bar into the model to train our model? Not really, right? Because if we did that, then how do we know that our model can do well on new data that we haven't seen? Like if I were to create a model to predict whether or not someone has diabetes, let's say that I just train all my data and I see that on my training data it does well. I go to some hospital, I'm like, here's my model. I think you can use this to predict if somebody has diabetes. Do we think that would be effective or not? Probably not, right? Because we haven't assessed how well our model can generalize. Okay, it might do well after, our model has seen this data over and over and over again. But what about new data? Can our model handle new data? Well, how do we get our model to assess that? So we actually break up our whole data set that we have into 3 different types of data sets. We call it the training data set, the validation data set, and the testing data set. And you might have 60% here, 20% and 20%, or 80, 10, and 10. It really depends on how many statistics you have. I think either of those would be acceptable. So what we do is then we feed the training data set into our model. We come up with, this might be a vector of predictions corresponding with each sample that we put into our model. We figure out, okay, what's the difference between our prediction and the true values? This is something known as loss. Loss is, what's the difference here in some numerical quantity, of course. And then we make adjustments, and that's what we call training, okay? So then, once, we've made a bunch of adjustments, we can put our validation set through this model. And the validation set is kind of used as a reality check during or after training to ensure that the model can handle unseen data still. So every single time after we train one iteration, we might stick the validation set in and see, hey, what's the loss there? And then after our training's over, we can assess the validation set and ask, hey, what's the loss there? But one key difference here is that we don't have that training step. This loss never gets fed back into the model, right? That feedback loop is not closed. All right, so let's talk about loss really quickly. So here I have 4 different types of models. I have some sort of data that's being fed into the model and then some output. Okay, so this output here is pretty far from, this truth that we want. And so this loss is going to be high. In model B, again, this is pretty far from what we want, so this loss is also going to be high. Let's give it 1.5. Now this one here, it's pretty close. I mean, maybe not almost, but pretty close to this one. So that might have a loss of 0.5. And then this one here is maybe further than this, but still better than these two. So that loss might be 0.9. Okay, so which of these model performs the best? Well, model C has the smallest loss, so it's probably model C. Okay, now let's take model C after, we've come up with all these models and we've seen, okay, model C is probably the best model. We take model C and we run our test set through this model. And this test set is used as a final check to see how generalizable that chosen model is. So if I, finish training my diabetes data set, then I could run it through some chunk of the data and I can say, oh, like this is how it would perform on data that it's never seen before at any point during the training process, okay? And that loss, that's the final reported performance of my test set, or this would be the final reported performance of my model, okay? So let's talk about this thing called loss, because I think I kind of just glossed over it, right? So loss is the difference between your prediction and the actual like label. So this would give a slightly higher loss than this. And this would even give a higher loss because it's even more off. In computer science, we like formulas, right? We like formulaic ways of describing things. So here are some examples of loss functions and how we can actually come up with numbers. This here is known as L1 loss. And basically L1 loss just takes the absolute value of whatever your, real value is, whatever the real output label is, subtracts the predicted value and takes the absolute value of that. Okay? So the absolute value is a function that looks something like this. So the further off you are, the greater your loss is, right? In either direction. So if your real value is off from your predicted value by 10, then your loss for that point value is whatever the real output label is, subtracts the predicted value and takes the absolute value of that. Okay, so the absolute value is a function that looks something like this. So the further off you are, the greater your loss is, right? In either direction. So if your real value is off from your predicted value by 10, then your loss for that point would be 10. And then this sum here just means, hey, we're taking all the points in our data set and we're trying to figure out the sum of how far everything is. Now, we also have something called L2 loss. So this loss function is quadratic, which means that if it's close, the penalty is very minimal. And if it's off by a lot, then the penalty is much, much higher. Okay? And this, instead of the absolute value, we just square the difference between the two. Now there's also something called binary cross entropy loss. It looks something like this, and this is for binary classification. This might be the loss that we use. So this loss, I'm not gonna really go through it too much, but you just need to know that loss decreases as the performance gets better. So there are some other measures of performance as well. So for example, accuracy. What is accuracy? So let's say that these are pictures that I'm feeding my model, okay? And these predictions might be apple, orange, orange, apple. Okay, but the actual is apple, orange, apple, apple. So 3 of them were correct and 1 of them was incorrect. So the accuracy of this model is 3/4 or 75%. All right, coming back to our Colab notebook, I'm going to close this a little bit. Again, we've imported stuff up here. And we've already created our data frame right here. And this is all of our data. This is what we're going to use to train our models. So down here, again, if we now take a look at our data set, you'll see that our classes are now 0s and 1s. So now this is all numerical, which is good because our computer can now understand that. Okay. And it would probably be a good idea to maybe kind of plot, hey, do these things have anything to do with the class? So here, I'm going to go through all of the labels. So for label in the columns of this data frame, so this just gets me the list. Actually, we have the list, right? It's called, so let's just use that. It might be less confusing. Of everything up till the last thing, which is the class. So I'm going to take all these 10 different features and I'm going to plot them as a histogram. And now I'm going to plot them as a histogram. So basically, if I take that data frame and I say, okay, for everything where the class is equal to 1, so these are all of our gammas, remember. Now, for that portion of the data frame, if I look at this label, so now these, okay, what this part here is saying is inside the data frame, get me everything where the class is equal to 1. So that's all of these would fit into that category, right? And now let's just look at the label column. So the first label would be f length, which would be this column. So this command here is getting me all the different values that belong to class 1 for this specific label. And that's exactly what I'm going to put into the histogram. And now I'm just going to tell, matplotlib, make the color blue, label this as, gamma, set alpha. Why do I keep doing that? Alpha equal to 0.7, so that's just like the transparency. And then I'm going to set density equal to true, so that when we compare it to the hadrons here, we'll have a baseline for comparing them. Okay, so the density being true just basically normalizes these distributions. So, if you have 200 of one type and then 50 of another type, well, if you drew the histograms, it would be hard to compare because one of them would be a lot bigger than the other, right? But by normalizing them, we kind of are distributing them over how many samples there are. All right, and then I'm just going to put a title on here, make that the label, the Y label. So because it's density, the Y label is probability. And the X label is just gonna be the label. What is going on? And I'm going to include a legend, and plt.show just means, okay, display the plot. So if I run that, just be up to the last item. So we want a list, right? Not just the last item. And now we can see that we're plotting all of these. So here we have the length. Oh, and I made this gamma. So this should be hadron. Okay, so the gamma's in blue, the hadrons are in red. So here we can already see that, maybe if the length is smaller, it's probably more likely to be gamma, right? And we can kind of, these all look somewhat similar. But here, okay, clearly if there's more asymmetry, or if, this asymmetry measure is larger, then it's probably a hadron. Okay, oh, this one's a good one. So F alpha, seems like hadrons are pretty evenly distributed, whereas if this is smaller, it looks like there's more gammas in that area. Okay, so this is kind of what the data that we're working with. We can kind of see what's going on. Okay, so the next thing that we're going to do here is we are going to create our train, our validation, and our test data sets. I'm going to set train, valid, and test to be equal to this, so numpy.split, I'm just splitting up the data frame. And if I do this sample, where I'm sampling everything, this will basically shuffle my data. Now, if I want to pass in where exactly I'm splitting my data set, so the first split is going to be maybe at 60%. So I'm just going to say 0.6 times the length of this data frame. So, and then cast that to an integer. That's going to be the first place where, I cut it off, and that'll be my training data. Now, if I then go to 0.8, this basically means everything between 60% and 80% of the length of the data set will go towards validation. And then like everything from 80 to 100 is going to be my test data. So I can run that. And now if we go up here and we inspect this data, we'll see that these columns seem to have values in like the 100s, whereas this one is 0.03, right? So the scale of all these numbers is way off, and sometimes that will affect our results. So one thing that we would want to do is scale these so that they are, so that it's now relative to maybe the mean and the standard deviation of that specific column. I'm going to create a function called scale dataset, and I'm going to pass in the data frame. And that's what I'll do for now. Okay, so the X values are going to be, I take the data frame, and let's assume that the columns are going to be, that the label will always be the last thing in the data frame. So what I can do is say data frame dot columns all the way up to the last item and get those values. Now for my Y, well, it's the last column, so I can just do this. I can just index into that last column and then get those values. Now, so I'm actually going to import something known as the standard scaler from sklearn. So if I come up here, I can go to sklearn.preprocessing, and I'm going to import standard scaler. I have to run that cell. I'm going to come back down here, and now I'm going to create a scaler and use that scaler. So standard scaler. And with the scaler, what I can do is actually just fit and transform X. So here I can say X is equal to scaler.fit transform X. So what that's doing is saying, okay, take X and fit the standard scaler to X, and then transform all those values, and what would it be? And that's going to be our new X. All right. And then I'm also going to just create, the whole data as one huge 2D NumPy array. And in order to do that, I'm going to call hstack. So hstack is saying, okay, take an array and another array and horizontally stack them together. That's what the H stands for. So by horizontally stack them together, just like put them side by side, okay, not on top of each other. So what am I stacking? Well, I have to pass in something so that it can stack X and Y. And now, okay, so NumPy is very particular about dimensions, right? So in this specific case, our X is a two-dimensional object, but Y is only a one-dimensional thing. It's only a vector of values. So in order to now reshape it into a 2D item, we have to call numpy.reshape, and we can pass in the dimensions of its reshape. So if I pass in -1, 1, that just means, okay, just at this one, I say I'm gonna fill in, and it would probably be a good idea to maybe kind of plot, hey,
Kylie Ying has worked at many interesting places, such as MIT, CERN, and Free Code Camp. She's a physicist, engineer, and basically a genius. And now she's going to teach you about machine learning in a way that is accessible to absolute beginners.
What's up, you guys? So welcome to Machine Learning for Everyone. If you are someone who is interested in machine learning and you think you are considered as everyone, then this video is for you. In this video, we'll talk about supervised and unsupervised learning models. We'll go through maybe a little bit of the logic or math behind them, and then we'll also see how we can program it on Google Colab. If there are certain things that I have done and you're somebody with more experience than me, please feel free to correct me in the comments, and we can all as a community learn from this together. So with that, let's just dive right in. Without wasting any time, let's just dive straight into the code, and I will be teaching you guys concepts as we go. So this here is the UCI machine learning repository, and basically they just have a ton of data sets that we can access. And I found this really cool one called the Magic Gamma Telescope data set. So in this data set, if you don't want to read all of this information, to summarize what I think is going on, is there's this gamma telescope, and we have all these high energy particles hitting the telescope. Now there's a camera, there's a detector that actually records certain patterns of how this light hits the camera, and we can use properties of those patterns in order to predict what type of particle caused that radiation. So whether it was a gamma particle or some other hadron. Down here, these are all of the attributes of those patterns that we collect in the camera. So you can see that there's, some length, width, size, asymmetry, etc. Now we're going to use all these properties to help us discriminate the patterns and whether or not they came from a gamma particle or a hadron. So in order to do this, we're going to come up here, go to the data folder, and you're going to click this Magic04 data, and we're going to download that. Now over here, I have a Colab notebook open. So you go to colab.research.google.com, you start a new notebook, and I'm just going to call this the Magic data set. So actually, I'm going to call this for CodeCamp Magic example. Okay. So with that, I'm going to first start with some imports. So I will import, I always import NumPy. I always import pandas. And I always import matplotlib. And then we'll import other things as we go. So yeah. We run that. In order to run the cell, you can either click this play button here, or you can, on my computer, it's just Shift Enter, and that will run the cell. And here I'm just going to let you guys know, okay, this is where I found the data set. So I've copied and pasted this actually, but this is just where I found the data set. And in order to import that downloaded file that we got from the computer, we're going to go over here to this folder thing. And I am literally just going to drag and drop that file into here. Okay. So in order to take a look at, what does this file consist of? Do we have the labels? Do we not? I mean, we could open it on our computer, but we can also just do pandas read CSV, and we can pass in the name of this file. And let's see what it returns. So consist of, do we have or a hadron? And we have a magic. I'm going and I always import matplotlib. And then we'll import other things as we go. So yeah. We run that. In order to run the cell, you can either click this play button here, or you can, on my computer, it's just Shift Enter, and that will run the cell. And here I'm just going to let you guys know, okay, this is where I found the data set. So I've copied and pasted this actually, but this is just where I found the data set. And in order to import that downloaded file that we got from the computer, we're going to go over here to this folder thing. And I am literally just going to drag and drop that file into here. Okay. So in order to take a look at, what does this file consist of? Do we have the labels? Do we not? I mean, we could open it on our computer, but we can also just do pandas read CSV, and we can pass in the name of this file. And let's see what it returns. So it doesn't seem like we have the label. So let's go back to of this file. And let's see. And we can pass in the name of this file. And let's see what it return. Pass in the consist of. Do we have the labels? Do we not? I mean, we could open it on our computer, but we can also just do pandas read CSV, and we can pass in the name of this file. And let's see what it returns. So it doesn't seem like we
Hi everyone, this is Vikas. I welcome all of you in third video tutorial for the Panda series, and here we would see how to load CSV file. So basically it is a comma separated value files, and it is also a Excel file only, but it has an extension of .csv. So today's our agenda is how to load CSV file, okay, or CSV data set. So please don't confuse with file or data set, because it contains information, right? So which contains information and which we want to use, that would be considered as a file or data set. Now first of all, we have to import the pandas. So what we'll write, import pandas as PD. Okay, once we execute, then this package is loaded. Then we will try to load the data set. So in this case we have to write pd.read underscore, and earlier we have seen for the Excel file which has an extension, I'll just write Excel file has a extension of .xls or .xlsx. So we had used pd.read underscore excel, okay, but in this case we should not use excel and we have to use .csv, okay. So I'll just remove this, and thereafter we have to write the file name, and of course we have to write the extension because this is a CSV file, so extension will be CSV, and then we execute this. So now we have to check the file name first, and this is my file name, which is Annual Enterprise Survey 2019 Financial, right? So see here, it also shows this is a Microsoft Excel for housing underscore Excel. For the earlier tutorial we have seen, so you can see both are Microsoft Excel file only, but both having different extension, okay. So now I'll select this Annual Enterprise Survey, right click and go for the properties. You can also do the same thing, and here you can just check this out. This file has a very long name, right? It has a very long name. So what we can do, we can just
have the label. So let's go back to here. I'm just gonna make the, let's can also just do pandas read CSV, and we can pass in the name of this file, and let's see what it returns. So it doesn't seem like we have the label, so let's go back to here. I'm just gonna make the columns, the column labels, all of these attribute names over here. So I'm just gonna take these values and make that the column names. All right, how do I do that? So basically, I will come back here and I will create a list called calls, and I will type in all of those things. With f size, f conc, and we also have f conc 1. We have f symmetry, fm3 long, fm3 trans, f alpha. What else do we have? F dist and class. And class. Okay, great. Now, in order to label those as these columns down here in our data frame, so basically this command here just reads some CSV file that you pass in. CSV is comma separated values, and turns that into a pandas data frame object. So now if I pass in a names here, then it basically assigns these labels to the columns of this data set. So I'm gonna set this data frame equal to df, and then if we call, so head is just like, give me the first 5 things. Now you'll see that we have labels for all. I'm gonna set this data frame equal to df, and then if we call, so head is just like, give me the first 5 things. Now you'll see that we have labels for all of these, okay? All right, great. So one thing that you might notice is that over here, the class labels, we have G and H. So if I actually go down here and I do data frame class.unique, you'll see that I have either G's or H's, and these stand for gammas or hadrons. And our computer is not. So if I actually go down here and I do data frame class.unique, you'll see that I have either G's or H's, and these stand for gammas or hadrons. And our computer is not so good at understanding letters, right? Our computer is really good at understanding numbers. So what we're going to do is we're going to convert this to 0 for G and 1 for H. So here I'm going to set this equal to this, whether or not that equals G, and then I'm just going to say as type int. So what this should do is convert this entire column. If it equals G, then this is true, so I guess to 0. You'll see that I have either G's or H. What you might notice is that over here, the class labels, we have G and H. So if I actually go down here and I do data frame class.unique, you'll see that I have either G's or H's, and these stand for gammas or hadrons. And our computer is not so good at understanding letters, right? Our computer is really good at understanding numbers. So what we're going to do is we're going to convert this to 0 for G and 1 for H. So here I'm going to set this equal to this, whether or not that equals G, and then I'm just going to say as type int. So what this should do is convert this entire column. if it equals G, then this is true, so I guess that would be 1. And then if it's H, it would be false, so that would be 0. But I'm just converting G and H to 1s and 0s. It doesn't really matter like if G is 1 and H is 0 or vice versa. Let me just take a step back right now and talk about this data set. So here I have some data frame and I have all of these different values for each entry. Now this is each of these is one sample. It's one example. It's one item in our data set. It's one data point. All of these things are kind of the same thing when I mention, oh, this is one example or this is one sample or whatever. Now, each of these samples, they have, one quality for each or one value for each of these labels up here, and then it has the class. Now, what we're going to do in this specific example is try to predict for future, samples, whether the class is G for gamma or H for hadron. And that is something known as classification. Now, all of these up here, these are known as our features. And features are just things that we're going to pass into our model in order to help us predict the label, which in this case is the class column. So for, sample 0, I have 10 different features. So I have 10 different values that I can pass into some model, and I can spit out, the class, the label. And I know the true label here is G, so this is actually supervised learning. All right. So before I move on, let me just give you a quick little crash course on what I just said. This is machine learning for everyone. Well, the first question is, what is machine learning? Well, machine learning is a subdomain of computer science that focuses on certain algorithms which might help a computer learn from data without a programmer being there telling the computer exactly what to do. That's what we call explicit programming. So you might have heard of AI and ML and data science. What is the difference between all of these? So AI is artificial intelligence, and that's an area of computer science where the goal is to enable computers and machines to perform human-like tasks and simulate human behavior. Now, machine learning is a subset of AI that tries to solve one specific problem and make predictions using certain data. And data science is a field that attempts to find patterns and draw insights from data. And that might mean we're using machine learning. So all of these fields kind of overlap, and all of them might use machine learning. So there are a few types of machine learning. The first one is supervised learning. And in supervised learning, we're using labeled inputs. So this means whatever input we get, we have a corresponding output label in order to train models and to learn outputs of different new inputs that we might feed our model. So for example, I might have these pictures, okay? To a computer, all these pictures are pixels. They're pixels with a certain color. Now in supervised learning, all of these inputs have a label associated with them. This is the output that we might want the computer to be able to predict. So for example, over here, this picture is a cat, this picture is a dog, and this picture is a lizard. And in unsupervised learning, we use unlabeled data to learn about patterns in the data. So here are my input data points. Again, they're just images, they're just pixels. Well, okay, let's say I have a bunch of these different pictures. And what I can do is I can feed all of these to my computer, and I might not, my computer's not gonna be able to say, oh, this is a cat, dog, and lizard in terms of, the output, but it might be able to cluster all of these pictures. It might say, hey, all of these have something in common. All of these have something in common. And then these down here have something in common. That's finding some sort of structure in our unlabeled data. And finally, we have reinforcement learning. And reinforcement learning, well, there's an agent that is learning in some sort of interactive environment based on rewards and penalties. So let's think of a dog. We can train our dog, but there's not necessarily, any wrong or right output at any given moment, right? Well, let's pretend that dog is a computer. Essentially, what we're doing is we're giving rewards to our computer and telling our computer, hey, this is probably something good that you want to keep doing. Well, computer agent, terminology. But in this class today, we'll be focusing on supervised learning and unsupervised learning and learning different models for each of those. All right, so let's talk about supervised learning first. So this is kind of what a machine learning model looks like. You have a bunch of inputs that are going into some model, and then the model is spitting out an output, which is our prediction. So all these inputs, this is what we call